All right, let's jump right in. We are about to go on an architectural journey, you and I. We're on the hunt for a single, fundamental blueprint, a pattern that seems to dictate how pretty much everything gets put together, from a simple line of code all the way up to the cosmos itself. It's this universal logic of composition, and trust me, once you see it, you are going to start seeing it absolutely everywhere.
So let's start somewhere practical, the world of business. You've probably heard the buzzword, right? The composable enterprise. And the idea is it's pretty simple. Think of it like a big box of Lego bricks. The idea is you break a company down into these independent, reusable chunks. The fancy term is packaged business capabilities. And then you can just snap them together in all sorts of new ways to build new products, new services, super fast.
But here's the question that really kicks off our entire exploration. Is this Lego brick model just a clever business strategy? Or is it a glimpse of something much, much deeper? A kind of universal truth about how everything is built? Well, to even start to answer that, we've got to go deeper, way deeper, right down into the mathematical bedrock of reality itself.
To get our bearings, let's look at another system of composition that we all know pretty well, chemistry. You've got your basic elements, right? Your atoms and your molecules, and then you have rules for how they combine. We call them chemical reactions. You take simple parts, you combine them, and they form substances with totally new properties. That's composition in action. It's a perfect place to start.
Now, to properly describe this universal pattern, we need a special language, and that language is called category theory. What's so wild about it is that it doesn't really care about the things themselves, the individual Lego bricks or the atoms. No, it cares about the relationships and the connections between them. So in this language, the things are called objects. A hydrogen atom? That's an object. A blue Lego brick? That's an object too. The connections, the rules for how you can change one thing into another, those are called morphisms. Just think of them as arrows. It's the mathematics of how things relate to each other.
Okay, so if you're building with Legos, you can do two basic things, right? You can snap one brick on top of another. That's connecting them in a sequence. But you can also just place two bricks side by side ready to be used. Well, that simple act of putting things next to each other, in parallel, is incredibly important. In category theory, the structure that allows for this is called a symmetric monoidal category, and it gives us a special operation for that side-by-side action called the tensor product. That's that little O symbol. You can just think of it as the official mathematical way of saying and. It lets us consider two things at once, even before they've actually interacted.
And this slide, this shows you exactly what that looks like. You can literally draw these systems out like wiring diagrams. The wires, those represent our objects. Our resources are stuff. And those little boxes they pass through, those are the morphisms, the processes that change them. The tensor product we were just talking about, that's just what happens when you place two wires next to each other. And connecting one box after another, well, that's just sequential composition. It's a really simple visual language, but it's powerful enough to map out pretty much anything.
And here is the absolute crucial point. This is not just some abstract mathematical game. It is a direct description of how reality works. This quote makes it crystal clear. Any theory of resources, doesn't matter if it's chemistry or thermodynamics or even economics, is a symmetric monoidal category. The resources are the objects, the transformations are the morphisms. The math and the reality, they're one and the same.
But here's where our perfect orderly blueprint runs into a problem, a really big one. Because when we actually connect these systems together in the real world, things get weird. As Eli Adam from MIT points out here, the properties that we so carefully designed into our individual components can suddenly start to behave very badly once they start interacting. The whole, it turns out, is often bizarrely, unpredictably different from the sum of its parts. And that is the central challenge of all engineering, from a tiny circuit to an entire society.
We actually have a name for this phenomenon: generative effects. These are the emergent behaviors, the cascading failures, the unexpected contagions that just seem to pop into existence when you combine systems. Formally, it just means that the observable properties of the combined system, they're not equal to the sum of the observable properties of the individual systems. Something brand new and often unpredictable has been generated in the process. Think of it like this. Over on the left, we have our components, all by themselves. We can test them, we can measure them, we know exactly how they behave. But on the right, that's what happens after we connect them. All of a sudden, new properties emerge that just weren't there before. This gap, right here, between the predictable parts and the unpredictable whole, is where everything interesting happens. It's the source of catastrophic failure, but it's also the source of breakthrough innovation. It's kind of like the ghost in the machine.
So where do these mysterious generative effects actually come from?
The theory offers this really beautiful and powerful idea, a veil. The concept is that for any system, there's a separation between what we can see and measure on the outside and all of its hidden inner workings. So when we combine two systems, it's those concealed mechanisms that start to interact behind the veil in ways we can't see or predict. And every now and then, the results of those hidden interactions burst through the veil as a new emergent property in the world we can see.
So what's the mathematical root cause of all this? It's a concept called a loss of exactness. Think of it this way. When we only look at the outside of a system, when we apply that veil, we are, by definition, losing some information about its internal complexity. The map is not the territory. And it's right there, in that gap, in that lost information, that the space for unpredictable generative effects is created. That is the formal reason for emergence.
Okay, I know this all sounds incredibly abstract, but understanding this deep structure gives us an extraordinary power, the ability to engineer systems better. If we can understand the blueprint, we can become master architects. So the question is, how do we translate all this theory into practice? Well, the key tool we use for this is called a functor. Now, if a morphism is an arrow that connects things inside of one system, a functor is like a bigger arrow that connects entire systems to each other. Think of it like Google Translate, but for system designs. It lets you take a blueprint from one language, say a conceptual model you drew on a whiteboard, and translate it into a completely different language, like software code, while guaranteeing that the core structure and all the relationships are perfectly preserved. It's our universal blueprint translator.
And this leads us to a really practical engineering workflow. We call it the concept, model, graph, view cycle. You start with a concept, an idea. You use a functor to translate that into a formal model in a specific language. Then you use another functor to translate that model into a universal graph data structure. And from that one universal graph, you can apply even more functors to generate any view you need: diagrams, matrices, reports, each one tailored for different stakeholders.
Now look closely at this diagram. This is where the pattern gets really truly mind-bending, because it's fractal. What you're looking at here is the blueprint for a system design language itself. The parts of the language, things like object and process, they are themselves the objects of a category, and the rules for how you can connect them, those are the morphisms. This means the very tools we use to design our systems are also built from the exact same universal blueprint. It is composition all the way down.
So let's bring this journey home. We started with a simple idea from the business world, the composable enterprise, built like Lego. We then journeyed into the deepest foundations of mathematics to understand why that idea is so powerful.
And now we can come back to that composable enterprise and describe it with a new, powerful precision. Those autonomous building blocks, they're objects. The APIs that connect them, those are morphisms. Assembling a new customer journey, that's composition. Managing parallel capabilities, that is precisely the Tensor product. And most importantly, we realize we're not just designing the parts anymore. We are architecting the whole, consciously designing for the powerful and inevitable effects of emergence.
We've seen this blueprint scale from abstract math all the way to concrete software, from a single tiny component to a massive global enterprise. It really does appear to be a universal pattern for creating complexity and intelligence. So that leaves us with one final vast question. If this truly is the blueprint for composition, and we are just now learning how to become its architects, what should humanity compose next?